welcome. I'm happy to see so many people coming here to spend your time to listen to me talk about a little bit of our high-perform products of Milliken. So today I'm not going to talk about a specific product. Rather, I want to give you guys a little bit more broad view on the nucleators and talk about what is nucleator, why does it matter, and there are a bunch of different nuclear technologies in the market to see why Milliken's nuclear is unique, is different in what way, and help the customers and our customer's customer in what way. Let's jump into that. Why nucleators matter? Why we are talking about nucleators? Nuclear is only a small component of the final part. It's only like in typical form range is around 0.05% of the final components. It's a very small part of the final components, but it plays a crucial role. It impacts a variety of material performance of a polypropylene. It increases TC significantly. Increasing TC, what does it really mean? Increasing TC normally depends on the conversion technology. Normally what that means, it will reduce cycle time. It reduces the cooling temperature, cooling time. That means the cooling of the part starts earlier. The parts get to the final form better in a faster time. It alters shrinkage. It's not like reduce the shrinkage, but it alters the three-dimension shrinkage in a different way. And it works in our way, in our high-perform nucleator is specifically known for this isotropic shrinkage. Isotropic shrinkage meaning it shrinks in the both machine and cross-machine direction similarly. That helps to reduce the scraps. That was one of the reasons why a lot of converters will have the part that is warped. Warpage is called part scrap. So this isotropic shrinkage, to control the shrinkage well, can improve the product quality. Nuclear can also increase the stiffness, increase the modulus. And increasing modulus, it can have two effects. One, you just have a better product. Some applications, especially of some intermaterial replacement opportunities that PP is not stiff enough, with stiff nucleated PP, then you can have a chance to some applications to replace other engineered polymers. Or if there is a certain given modulus that we need to reach as a part, with nucleated PP, you can reduce the thickness of the part, still reaching the same performance. So that will be the cost saving in the case, right? HDT, heat detortion temperature. This is becoming also quite important. A lot of applications of our final parts are used in various applications, like automotive goes into close to the combustion engines that you need a heat detortion temperature. And some food applications, more and more now people are using plastic packaging directly go to microwave, and you need to withstand heat. So heat distortion temperature, to have a higher heat distortion temperature, it's definitely a clear value proposition. To a fact that my last Japan expo, I saw a Japanese customer is using a PP that is have 150 Celsius HDT value for the food packaging, and they want to have a fast steam process in the convenience store chain. So HDT, it can be improved by a nucleator as well. Another one is optics. That one, perhaps you all know about the clarifier, who can increase the optics, make the parts less hazy, more transparent. Nuclear can do the same, but to the different level, not to the same level as clarifier, because it has other performance, but in the same time can also. So nucleator also improves the optical performance of the PP. From comparing to the non-nucleated PP, the nucleated PP of a homo PP can significantly improve the haze performance, not to the level of clarifier, but definitely much better visually than non-nucleated PP. And all of that means with the nucleator, you have chance to improve the productivity, and also in the same time have a better quality and material saving. So nucleators is important, but how the nucleator is improving the PP's performance, how the mechanism behind it is working. In a simple form, to understand that, the key is to understand the crystal growth of PP. PP is a semi-crystalline polymer. There is crystals inside. The crystals start to grow when the PP start to cool down, right? So let's see if there is a no nucleator scenario, how the crystal is forming and how the crystal is growing. So the PP is being heated up during the extrusion and then become a liquid form, go to the mold, go to the shape and form that we want, and then start to cool down. When it cools to, we call it crystallization temperature, the crystals start to grow. The first crystal, they start to grow randomly in different locations at different times. Some will start a bit earlier, some will start a bit later, and all the PP part will start to crystallize in different locations at different speed. So that will have it's in a microscope. If you look at it, it's kind of a sphere, a bowl-like shape, like this, but it will have a different size. By the time it cools further, it will have more crystals, and the crystal will have different shapes. That is pure random how it grows, and some will be big, some will be small. But this crystal, it's a key for the performance of PP. How big or how small it is impacts optical performance. The direction of that and how it's been aligned also affect the physical performance of that. So how the nucleator PP works is, in the resin, we put a particle that can withstand a very high amount of heat, that can withstand a very high temperature that does not melt, right? So when the PP melts, our nucleator particles will not melt, and we evenly disperse it in the entire liquid, right? So when you melt the PP, you will have a solid nuclear particles in that. This is for the illustration, but in reality, in a small area like this, perhaps you find one nucleator particle, not this much, right? But then the nucleators, how the nucleator help for the crystal grow is the crystal will start to grow just around our nucleators, just around that particle. It will be a platform for the crystal to start grow. It's like we have the seed, and then the tree start to grow from that point. And because we have all these particles spread, almost all the particles will grow, the crystal will grow around a similar time. And during the similar time, it will grow to the similar size. And the size in general, you don't find very small crystals, but you also don't find very large crystals. We don't want large crystals. The reason we don't want large crystals is because the large crystals will reflect the light that will make your PP hazy. That will be not transparent. So we can reduce the size of crystals and make it, so what nuclear does is we induce the crystals to grow in a way that to the level that we can control, to make sure the crystal grow to a certain size and shape that we want it to go. Right? Clarify, on the other hand, does not have a solid particle when it's melt, but when it cool down, before the PP itself starts to form a crystal, our clarifier first form a line like crystals like this, and then PP will form crystals on top of that. So it's a bit similar story, but in this case, it's a soluble. And then first, our clarifier will form, and then the crystals will form on top of this. So that's the difference between clarifier and nucleator. And that's how the nucleator works. And nucleator, there are a bunch of different technologies. And within the different nucleators, because it's all impacting the crystal growth, right? Using this crystal growth, influencing the crystal growth to have a balanced performance of all these parameters, it's a balancing act. So sometimes you have a very strong stiffness, but then in the contrary, you will lose impact. Sometimes you have a very high crystallinity, but sometimes your some other parts shrinkage or some other things is not balanced, because this is very difficult to have one nucleator that is good in everything. But especially in this case, I'm taking the example of, most importantly, the customer, when talking about stiffness improvement, they are talking about stiffness improvement without losing impact. Because if you want to have stiffness improve, you put a lot of, for example, cheaper filler like talc. It can improve stiffness dramatically, but in the same time, you lose your impact. The parts become too brittle. Now, with nucleator, you can increase stiffness, the modulus, significantly, while the impact is not influenced or influenced very, very minimally. So that is the benefit of using nucleator, because of the crystal growth that can improve the stiffness without impacting the impact performance. This is an illustration of how the TC works. Right? So when it extrudes, you will have a high temperature. The PP start to melt around 160, 165, and then go to 220 or 230 when it starts to cool down, when the part is being formed. At some point you will start to have the crystal starting to grow. That is what we call crystallization temperature. If you have questions, just ask me. And if it's not nucleated, the crystallization temperature will start a bit late. In this case, around 115, 114 degrees C, right? But if it's nucleated, in this case, nucleated with our a higher TC product, it can start to nucleate at 127, 128 C. That makes a big difference between 127 and 115. That degree of difference of TC, that means you can be in the production cycle much faster. You can make more parts in the same time. Because of cooling, it's the real bottleneck of how fast the conversion of parts can be made. Cooling takes more time. If you take it out from the mold without being properly cool, the part just will warp. So it will not work properly. But you can see there are different types of nucleators, right? And one will differ from another in terms of TC. And we have one nucleator that is giving the best TC in the industry for the specific application. This is to illustrate isotopic shrinkage. The shrinkage if you think about shrinkage of a PP resin or a part, it's three-dimensional. It's machine direction, cross-machine direction, and the normal direction. And normally the PP itself shrinks in all directions together when it gets heat. But with the nucleator, because we control the crystal growth and the crystals start to grow in a certain direction, not only the size is different, the direction is different. So we were able to say it shrink less in the machine and cross-machine direction, and both directions shrinks a little bit similar. So in that case, compared to control, our shrinkage is very comparable in terms of isotropic shrinkage. This helps when the parts is a bit complex. You need to be very flat, and especially thinking about some lids, very thin lids. If you don't control the shrinkage well, when the part's being made, some part will be slightly warped, and it will be not good quality. These are some examples on the isotopic shrinkage. This is on the isotopic shrinkage. This one, I can please. And this is what we call pigment leveling. This is related to TC. When the nucleator is being used in the caps enclosure, if you have a blue pigment inside, especially blue or green colors, blue pigment itself works as a nucleator as well. It's just not a good nucleator, but it works as a nucleator. So it starts to outperform your own nucleator, and then you have a different shrinkage when you have a different color of caps. In a production, that's what you don't want. So if you have a higher TC than the blue pigment, the nucleator works faster, then we can outperform that. Using our nucleator, you will not have problem. All the caps will be a certain size. And this is example of how the shrinkage control can help for the automotive. In a bumper application, we heard from the customer that shrinkage control there is also very important. They specifically look for CLTE. CLTE, remind me, coefficient. Yes, that is important because when the bumper is being made, the car goes to a hotter or colder environment. You don't want the bumper to expand or shrink too much. But because PP in general, in nature, will expand and shrink, car makers always put a small gap between bumper and another part. So otherwise, if it starts to expand, you'll start to fight each other. It will have problem. So if you have a better CLTE for the premium car, they don't like that gap. It looks ugly and it's not good aerodynamic. So if you have a good CLTE, they can reduce that gap. So this is also the application why nucleator is helpful in automotive. Yeah, I want to mention one point is our nucleator is being validated by UL label as energy saving. It's globally validated for most of our product in high performance. If you use that, the converters during the production can save energy. Right. So as I said, nucleators works in improves different variety of different performance of the PP. Because of that, it works in a variety of applications. As we can imagine, it works in injection molding, thin wall, injection molding, thermoforming, ECM, automotive, pipe. We have many applications in different parts of the industry. Today, I specifically want to mention one part is the thin wall injection molding application. We see that it's an interesting market for India. This was the growth engine for PP industry in China for the last 10 years. This industry grew in average every year by 30% plus since 2014 till 2024. A lot of PP makers the business the volume increased a lot because of this application. This application is mainly we are the co-developer of this grade in China at the time. We introduced that with our customer, and it's been a success. The reason why is because it also comes with a fast growth of online food delivery. I guess that's also coming more and more in India, like Uber Eats. These are similar platforms. And the reasons why they moved away from lower quality thermoforming to injection molding is because the injection molding has to have a certain stiffness, and it has to the lid and the cup itself have to seal very well, because a lot of food in China it's liquid, it's hot and liquid. And I think it's similar story in India. There's a lot of food that is very oily with a lot of sauces. If we want to deliver that with thermoforming with less thickness, during the transportation, it splits. That's why the market moved, and we are already seeing a lot of interest in this market, and we are having some projects with some customers in India about thin wall injection molding packaging. And that is it's going to high melt flow homo PP. we are seeing from 60 to going to 70 to going to 90 and plus even 100 MFR to get more and more speed, more and more faster cycle time. And isotropic shrinkage is definitely the key. Clarity is important because customers want to see what's inside. And also with our unique value of we call it AE package, it's our fresh looking visual. You don't see the PP package a bit yellowish. We see it real fresh. That is important to make your food inside looks a little bit appealing for the consumer. And this is the reason why our Millikan high performance nucleator was, and it still is the market leader in that segment. And we are really hopeful that for the Indian market, we can also supply with collaborate with our Indian customers to develop this market together. We have a variety of products, not only one, several products in this. I don't have time to go through each of the products today, but if you are interested, we can definitely share with you. That's it. That's all I want to share today. Thank you.